Hi everybody, I'm Toby. I'm an ocean engineer with Kelson Marine. And at Kelson, we have a fairly unique skill set designing and de-risking offshore seaweed farms. And a lot of that comes from our work with ARPA-E, where our job has been to develop the tools and techniques to accurately and efficiently predict the forces on these large structures in waves and currents. So because of that unique skill set, we get to work with clients around the world on designing seaweed farms. And several clients, when we've started working with them, have asked me, so is anyone making any money doing this? It's a hard industry that we've collectively picked. There's conflicting data about the profitability of seaweed, and it's even more controversial, the question of whether you can make money moving farming into deeper, more offshore, more exposed sites. And that's part of the question that we want to answer today. But before we can answer the question of whether offshore farming is economical, we have to answer the question, what is offshore? So I'm part of the IEC's working group on Open-Ocean Aquaculture. This is a group of farmers, engineers, scientists, and other stakeholders, some of whom are here in this room. And part of our mission has been to deliver clear, concise, and useful terminology so that stakeholders can effectively communicate risks, costs, and other data around offshore or open ocean or exposed seaweed farming. And take, for example, when we talk about this site, about the term offshore, take this site off the coast of Maine, where we've had several experimental farms over the past 5 years. It's just less than a kilometer from shore, but it's exposed to 6,000 kilometers of open ocean to the southeast. Are the economics of that site going to be the same as other nearshore sites? And after about 3 years of research and debating within this team, we came to one simple conclusion when it comes to defining this. We need to decouple the term offshore into two separate quantifiable metrics: distance from shore and exposure. Now, distance from shore is readily quantified. Exposure takes, we need to develop a new index to capture the complex interactions of currents, waves, water depth into a single number that stakeholders can use. And we actually proposed 6 different metrics that we've been evaluating and testing out. The first 2 are a straightforward combination of the design water current velocity and the wave-induced fluid dynamic velocity. The next is the specific exposure energy, which is essentially energy per unit mass, which conveniently is also proportional to drag forces, nominally, on structures. We also looked at 2 metrics, which are the depth integrated energy, or energy flux. Now, the first 4 proposed metrics here are exclusively depend on the site, and the last 2 also take into account the characteristic dimensions of the structure, where the last one is this. It's effectively the representation of the ratio of drag force to buoyant force on these components. For simplicity, I'm going to focus on one of these, which I also happen to like the best. But, and for a region, we're going to study the German Bight of the North Sea. And we're studying this area in particular because it's an area of interest for co-location with offshore wind parks. So distance from shore is shown on the left. But when we map that specific exposure energy for each site, what we find is kind of fascinating. So as we know, sheltered sites that are protected have low exposure energies. But most interesting to me is that the highest exposure energies actually happen in these near-shore sites that are exposed to large waves coming into shallow water, which create large horizontal fluid velocities, as well as where these constrictions create large tidal or storm-driven currents. And this is why we need to decouple the term offshore into distance from shore and exposure energy. Now, with that definition, let's look at a few sites. Going back to that initial site that I showed, that's just an easy half-kilometer steam from port, where we've been testing things like composite lines to mitigate whale entanglement, spatially dense farms, low-cost helical anchor installation technologies, and other novel technologies under the ARPA-E program. that nearshore site has an exposure energy of about 5 joules per kilogram. And this is a combination of strong storm-driven currents and large waves coming into shallow water. And we actually went ahead and mapped this not just for this site, but for about 30 different existing and proposed aquaculture sites around the world. And some of you in this room provided data for this, so thank you very much. And this is in an upcoming publication that you can look at in more detail. One of the drawbacks on combining all of this data into a single index is that you have to know some wave kinematics and calculate things like energy flux. So to make that easier, we've developed an online calculator. You can go to kelsonmarine.com/resources and put in your water depth and design conditions, and you can see where your site ranks on these 6 different metrics. Now that we've established some terminology around offshore or open ocean farming, we can start to look at the economics. So we're taking for this, for an example site, a site 16 kilometers off the coast of Maine. And this one was selected because it's being considered for a floating offshore wind installation as well. And we derived the current and wave design conditions as we do for all of these projects. And this one has an exposure energy of 7.1 joules per kilogram. So it's more exposed than the sites we've considered previously. Now, a quick note on defining those design conditions. I'll say this again and again, but when we look at the wave and the current velocities for a site, we don't design for the typical, even the 99th percentile or the 1-year storm. What we design for is the extremes, the 5, 10, and 50-year storms. And there's a world of difference between those two. So these exposure indices actually have a return period. So your mean exposure energy will be different from your 50-year exposure energy. So you can look at the characteristics of the sites. Another side note here. So we use fairly traditional, maybe slightly augmented ocean engineering techniques to apply these extreme values or estimate these extreme values. But one of the things, because we're in this really difficult industry where the margins are so tight, we've been exploring more and more how do we cut down the uncertainty around these design frameworks and drive down costs. So we've been working more and more with extreme probability contours. What we're showing here is the 10-year probability contour for the combination of significant wave height, period, and wind speed. And while we usually assume that peak wind speed and peak wave height happen on top of each other, and so their forces combine, what we're showing here is that they don't ever actually happen at the same time. And moving forward, we're trying to incorporate more and more of this into our design process and even into engineering guidelines so we can keep driving down those uncertainties and driving down costs. Now that we've defined those design characteristics for the site, we can get into actually designing the farm. And here we run into immediately the first challenge and the first impact on cost that happens with designing structures for far offshore deep water locations. Because we're in 100 meters of water, and because you need your mooring lines to be several times the water depth to keep the farm well tensioned, a basic farm design easily loses 80% of its area just to the moorings. And this is an effect that's usually neglected in published techno-economic analyses of large-scale offshore aquaculture. But commercially speaking, even when we're dealing with fairly large sites, this is always the constraint that we're balancing. How much grow line can we fit in a single area, and what is the trade-off between that and increasing forces on the moorings and anchors? So we looked at a range of different farm designs and aspect ratios designed to maximize the amount of biomass in each site. And there's a huge amount of optimization to do in just packing in as much grow line per area as possible. But the question then is, with those high aspect ratios farm that have more and more biomass in the farm, which economic factor dominates? Does having more biomass pay off, or does the increased force on the anchors and mooring lines drive your costs up so much that it becomes economically unfeasible? So the only way we can answer that is with these simulation techniques, so we can accurately predict the forces on these structures and calibrate the cost. So we did that for a range of farm designs. And here we get into the second and the distinct effect of farming in high exposure energies as opposed to offshore sites. In the large waves that are associated with these high exposure sites, we have to be really careful about spacing between lines. It does not work to take yield per grow line per hectare numbers from nearshore sites and just put those into offshore sites. Line-to-line interactions and potential biomass loss are a huge design constraint as we work on these very, very large farms. So we conducted this analysis on each of these different farm designs, went all the way through to details like sizing the anchors appropriately, taking into account the holding capacity, directional characteristics, etc., and got to the total cost of the components for each one of these structures. And what we found, of course, is that these farms are expensive. No surprise. And as expected, the largest, highest aspect ratio farm is much, much more expensive than the more traditional farms. But when we normalize by the amount of biomass that each farm can fit in the specified permit area, which is this constrained, which is the same for each one of these designs, we see a very different story. As we get to the larger, higher aspect ratios farms, the CapEx cost per biomass becomes more and more efficient. Now, I hope you're asking yourself the same question that all of our clients never ask us, even though they should ask us before they ever take any of our results for granted, and that is, how accurate are your models? The hydrodynamics of seaweed structures are complex. They don't fit standard engineering drag and added mass and hydrodynamic formulations. And we've done fairly extensive testing on full one-to-one scale models of macrocystis, saccharina, et cetera, in the tank. And because they don't fit traditional ocean engineering models, we've had to do this in custom software. I'm really grateful to ARPA-E for seeing the need for this. And what they've recently funded us to do is to take that whole workflow, which was previously tied to commercial solvers, and now implement this in open source solvers, so that we can have our non-traditional hydrodynamics, but also be able to optimize for speed. And right now where we're at is we're about 10 to 16 times faster than our old workflow. So if you're in this room and I've ever told you that you have to wait 2 weeks for a full set of dynamic results, those days are almost over. We're down to about a day for a full set of dynamic load cases. Now, speed is only good as your results are accurate. So how do we know that even with all these sophisticated simulation tools that we're actually predicting the right results? Well, we measure it at full scale in the ocean. And again, ARPA-E has been very helpful in funding these really difficult experiments. Partners like Ocean Rainforest and Trophic and others have been awesome collaborators as we actually measure the tensions on these farms while simultaneously measuring the waves and currents at these exposed sites. We've gotten to do this for saccharina, macrocystis, and a whole range of different sites and wave and wind and current conditions. And so far, we're within about 15% of our predicted values. And we're doing this at larger and larger scale. So this year, Ocean Rainforest in the US put out the first truly offshore farm in the US, which was really awesome to see. And this was particularly gratifying for us because we've been working with them on this for about 3 years, even talking with regulators to provide some assurance that this was designed properly, that it's robust and safe and worthy of being put off of state waters in California. And the Ocean Rainforest has done an amazing amount of work to make this happen. Again, all funded by ARPA-E. Now this site, incidentally, it's 6.6 kilometers from shore, and the exposure energy is about 6.6. Sorry, I'm a little bit frozen up here. Now there's tons to go into as when we start to look underwater at what happens at these farms in extreme storms. We could talk about the non-quadratic drag, we could talk about the wake dynamics or the low frequency mooring tensions. And what I've found as I've studied the physics of these farms for about 6 years is that hardly anyone ever really cares about the physics. So we'll bring it back to the economics. When we take all this, now that we have some confidence in these models, how does all this analysis tie into the actual cost of producing seaweed in exposed locations far from shore? Well, we took all of those results from our analyses of those different farm designs, put them into a very detailed and very rigorous economic model that was put together by Struan Coleman, who's now at World Wildlife Foundation. It includes everything from permitting costs, monitoring, anchor installation, not just anchor and mooring costs, as well as the financial costs of financing these farms, which is actually a very significant portion because this is a high CapEx expenditure. And where we got for the fairly optimized structural farm is a result of about $5,500 per dry metric ton farm gate, so prior to processing. Now, if we want to get a little bit more controversial, what happens if you want to do the same thing to sink the seaweed for carbon credits? Well, the first thing you have to do is you have to account for the seaweed or for the carbon that you are emitting in the process of growing the seaweed. And it turns out that almost 2/3 of the carbon that you sequester is actually offset by the carbon you emit in the process. It becomes a very, very difficult metric. So that drives the costs of these structures, or the levelized cost of carbon over a 30-year project to results that are 1 or 2 orders of magnitude higher than markets are paying right now. So how do we drive these costs down, whether it's for food, for fuel, or even for carbon? Well, there are a lot of steps that we need to make happen. So Scott Lindell and his team are working with this same group at the University of Maine to help improve the hatchery process and maximize the yield per meter of grow line. We need people to keep working on reducing labor costs. That's a huge driver of the costs. And what we're working on is the maximizing the farm design. So cutting down the uncertainty, cutting down the cost, and maximizing the amount of grow line in a given farm area while keeping the costs sustainable. So to wrap it up, or to summarize, we need to decouple distance from shore from exposure energy. That will help us communicate effectively between stakeholders, regulators, insurers, investors, farmers, engineers, scientists. Validation, to me, is everything. So when I say the physics of macroalgae don't follow standard ocean engineering tools, they actually don't scale with the non-dimensional numbers that we usually use to go from small scale to big scale, food number and Reynolds number. And that's why we do all of our validation in real-world, full-scale farms. And then lastly, to summarize, we cannot take numbers, whether it's yield per hectare or cost per ton, from nearshore cultivation or sheltered site cultivation and plug those into models for large-scale offshore or exposed aquaculture. As a side note, we've gotten some pushback in the US about using the term exposed. In general, Europeans are more comfortable with exposure than you Americans are, so I think we're okay. So what's next now? Well, we're part of a multi-year process now to do this techno-economic optimization. And to do this, we're closely coupling now the techno-economic model that Struan and the researchers at UMaine with the engineering so that we can keep finding these pathways toward economic viability. A side note, for you biologists and phycologists in the room, one thing we need is robust relationships between exposure energy and biomass and growth rates. Right now that's missing. There's anecdotal evidence, there's some conflicting evidence in the literature about when more exposure leads to higher growth rates and when more exposure leads to lower growth rates. We need good data so that we can really optimize this for these exposed open ocean sites. All this is, we're trying to enable this by allowing these, with these highly efficient, highly accurate numerical models that we are developing and validating. And then lastly, on the US side, we're working on new engineering guidelines specifically for low trophic shellfish and seaweed aquaculture to help drive down the uncertainty and drive down the risks, specifically for these low trophic cultivation structures. And we're hoping that will result in new engineering guidelines so that we can reduce that uncertainty, reduce the costs while maintaining structures and optimizing and improving structures that are safe, reliable, and economically feasible.